Alright. Let's continue. Okay. Where am I again? I think this one. We are in this homework, I think, right? Okay. And process run. Okay. Not this one. CPU intro. Okay, the seed is one, right? And then the process list, this one is 3 process. Again, x is the number of instruction. So 3 instruction, 50% probability whether it is a CPU process or the input-output process. Okay, something like this, and then okay, let's compare with this, right? Input output run immediate and input output run later. Switch on IO. Okay. Wait, what is switch? Okay. Uppercase S. Let's use switch on input output first, and then input output run later first because it is the default. This one. Okay. Run later like this. Alright. Okay, so maybe I want to intro, okay. I want to save the, what is it called? The process to compare later on. On IO run later, something like this maybe. And then okay, PID 0, PID 1. We're running the CPU, okay, right? And then this one is ready. Run IO later, okay. And then this one is This one is the I/O. This one is still ready, tapi ID1. This process 1. And this one block, right? You're running the CPU, okay. Running the CPU again. Running the CPU again. This one is done, I assume. And then, okay, so here they have 4, right? This is the 5th block state, and then run I/O again. Oh, wait a minute. This okay. This should be I/O done, if I remember correctly. We are running another I/O again, and then block, thing like this. Alright, maybe I should put this. Let's find out if we correct or not. Okay. Run CPU ready, right? Run I/O ready, okay, block. Run CPU done. Run I/O done, okay. Again. Okay. Oh, alright. We need another one. I'm not done. Okay. This is the run netra, right? Switch on, run immediate. This one. Immediate. Okay. Run CPU, okay. This one is ready, and then run the input, output, ready again. And then this one is blocked, right? Switch on input, output, okay. Run CPU, right? CPU again. And then I think this gonna be the same. Maybe. Okay. Done again. 5, okay. Run input output done. Again, run input output. Block. Alright. don't think it's gonna be different. I mean, again, the input-output is after we are done with the CPU process. Okay, let's find out. Okay. And CPU ready, okay. Right. There is no difference here. I mean, if it's gonna be a difference, maybe we can increase the instruction on the second process, something like that. Okay, now let's check this one. Switch on input output and switch on N. And okay. Let me change this. Switch on and run my trackers. I mean, if you're doing something like this, well, let's find out. And CPU, and then IT, and then IO, input output, right? This one is block, and CPU, okay, done. Alright. Wait, we're done, okay. Wait a minute. Switch on N. Switch on N. Okay. I think this should be ready instead. Because we haven't switched. Because if I remember correctly, this flag means that we are switching after the end of the process, right? This one. Not, where is it? Not this one. Or issue an input output, right? So we need to finish the input output process first, and then we can switch to the process 1. But yeah, I'm kind of curious. If we are done in here, do we switch to process 1, the PIT 1? Or we still continue? Maybe we are still continue. let's find out later on. But I think it will be something like this. We are finishing this one, right? Okay. Run. Put output done. And then I think we can do something like this. Or maybe it is still ready. And then this one is done. Run CPU. Maybe something like this. Let's find out. Okay. Run CPU, input output, okay, ready, done. Right. This one. Then input output again, okay. Okay, this one. We are still in the ready status. Okay, and then run the CPU. Okay, let me check the total. Okay, 18 time. Whatever this time measurement is. Alright, now switch on N, input output run immediately. I mean, if the input output is on the process 0, I don't think there is any difference. Let's find out, I guess. Switch on N. Immediate, okay. Yeah, I'm assuming there is no difference because the input output is on the first process, on the process 0, right? If the input output on the, what is it called? On the second process. Well, let's find out. Oh, okay. I think why it is not make a difference is because switch on N. We are finishing whatever on the process 0 is. Alright. Now what about letter sys on IO with the set 2. Okay. Alright, input output run letter CPU system will switch when the current process is finished. Okay. Yeah, the difference is maybe something like this, right? When we have this input output doing first and then okay, this look interesting. Let me check. Switch on and not on and not this is input output and input output run immediate. Okay, this one. This is the previous one. Alright. Run input output ready and then block right run CPU and then block again input output block again. Okay, this is 5, right? Okay, and then we're back to this. Input output done. This one is still blocked. Okay. Running again input output. Is this one still blocked? Block. Input output done. Okay. We are running again input output. Block. Okay. And then this one input output done. Still block. Run CPU. 3, 4, 5. Okay. This one is done. This one run not done. Maybe something like this. Right. Let me check. Okay, 16 time, right? Block, okay, done. Alright. Okay, if we use run letter, right, I think this gonna become, where is it? Run letter. Run IO. This one is ready, okay. Block. Run CPU, run IO, okay. This one is also block. And then this is 5. Block. Is it gonna become ready? Something like this maybe. We're waiting for this one. Okay. Okay, and then done. Maybe this one. I'm still not sure if this is correct or not. Okay. I mean, input output run later, right? If it is run immediate, we will move back to this one. But because it is run later, I think it is something like this. Done. I mean, I'm assuming the scenario might be similar to this one, you know. This is block, right? And we keep finishing the running process of process 1 in here. So even though we already finished the input output, we are not going back to the process 0. And then after the process 1 done, we are going back to the process 0. I'm assuming something like that. Output, input, output, okay. This is done. And then maybe this is something like output done. Then we're running again. Block. Okay. Maybe something like this. We will see. Okay. Block and CPU. Okay, block. Oh. Okay. Wait a minute. Even when we use run later. It is still the same. Interesting. So it's on input output. Oh, because it is block. Okay. Right. Yeah, because what is it called? The PID one is still blocked. That's why we are switching back. So if this one is CPU rather than the input output, we might not switch back to the process 0 and finish this. Okay. Like this. Alright. Let me check. Yeah, something like this. Now that make me wonder what happen if we use C3. This one. Okay. Put. Okay. I mean, if we are still using switch on input output, I think we will switch this back, right? We run this first. This is block and then running this, it's also block. And then when this is done, okay, when this is done, do we go back to the CPU or continue in this one? Okay, let's check that out. Input, output, run metal. Okay, this one. Run CPU, ready. Ready, okay. Block, and then run input, output, I guess. Block. Okay. 5, okay. And then switch on input output. Oh, do we go back like this? Then because we are still blocked, right? But this is exactly, what is it called? This is exactly the 5th. So after this, I also be done. Maybe something like this. Ready, run IO done. Okay. Then doing the IO again, maybe. Block. And this one run CPU, maybe. Something like that. This one is done. It is still blocked. Okay. Oh, done. And then we run the CPU. Something like this maybe. Let's find out. Okay, ready. Output block. Okay. Oh. Alright. Okay, so because we switch on input output, we are going back to the PID 0, the process 0. Okay. Alright. So, this one should be run CPU. This one should be ready. This one button run IO. Okay, just done, right? And this one block done. Okay, 18 time. Alright. Okay. And well, of course, if we change this to N, switch on N, gonna be different. See, it become ready. So we are literally trying to finish the process 0, the PID 0 here. After we finish this, we will move on to the PID 1. Something like that. Input output letter. Yeah, I kind of forgot. Put output letter. Okay, I think this is the one that not being effective, right? Let's try out. This I thought it, and then letter, not really 50-50. 0, which means that, where is it? This one, if y is 0, a process will only issue input output. We will only issue input output, and then 5 instructions for the CPU, and then another 5 instructions for the CPU. Something, okay, yes. Alright, something like this. Switch on IO run letter. Where is it? Okay, this one. When input output completes, the process that issued is not necessarily run right away. After whatever was running at the time keeps running. keeps running. And at the time keeps running. I mean, okay. So if this one is not input output, this input output run letter might, what is it called? Might not switch back to this one. Maybe. Okay, we will see this scenario. Okay, we're plugged in here, and then we run the CPU on the PIT1, and then run the CPU at the PIT2. Okay. Right, so if, where is it? If in this case, this process is not input-output but the CPU process, we might not switch back to the input-output. Like this one, it become ready instead of input-output done. Okay. So yeah, to make it more efficient, I think we can do something like this. Switch on input-output when we are plugged, right, like this one. And then if the input-output already done, we switch back to the input-output. Total time 21, this time total time 26. So we're plugged, right? And then we are switching back to the input-output. To input-output done. Well, the PIT1 already done, and then running again. The second input-output, and then we are running the PIT2. The process 2. It is the CPU process. And then, well, we just finish the input-output after that. Okay. Hello, Luigi. Welcome. How are you? Still the same, I guess. Sometimes what is it called? I'm still cooking. So, but overall, I'm still fine. Fortunately. Okay. Alright. I think we already done this. Yeah, I mean, it's not really much different, I guess, depending on where the input output is. and also the flag too. The flag will really have an effect depending on where the input output is. Is it on the process 0 or process 1, right? Okay, anyway, let's moving on to process API. Let me open the table of content. Okay, we already take a look at this. Right. Okay, I think this is the summary. This conceptual view in mind, we will now move on to the nitty-gritty, the low-level mechanism needed to implement process, and the higher-level policies required to schedule them in an intelligent way by combining mechanism and policies. Okay. We will put up our understanding of how an operating system virtualizes the CPU. Okay. We have the process list or task list, right? Process control block. Okay. Okay. Struct context. This is from the XV6 kernel. Data structure, okay. Yeah, maybe we will understand the register. Okay, no. So we will need to check what the register ourselves. Okay, well, I think let's moving on. Process descriptor. Key process term. The process is the major OS or operating system abstraction of a running program. At any point in time, the process can be described by its state, the contents of memory in its address space, the content of CPU register, including the program counter and stack pointer, among others, information about input-output. The process API consists of calls program can make related to processes. Typically, this includes creation, destruction, and other useful calls. Process exists in one of many different process states. Running, ready to run, and block. Different event, okay. Waiting for input output to complete. Transition a process from one of these states to the other, right? The state of the process. The process list. process in the system. Okay. Well, let's continue to this one. Process API. Aside interludes. Okay. Interludes will cover more practical aspect of system. Okay. Practical aspect of system, including a particular focus on operating system API and how to use them. If you don't like practical things, you could skip these interludes, okay? But you should like practical things because, well, they are generally useful in real life. Companies, for example, don't usually hire you for your non-practical skill. Okay. In this interlude, we discuss process creation in Unix system. Interlude, we discuss process creation in Unix system. Unix present one of the most intriguing ways to create a new process with a pair of system calls, fork and exec. Process creation in Unix system. The most intriguing ways to create a new process with a pair of system calls, fork and exec. A third routine wait can be used by a process wishing to wait for a process it has created to complete. Okay. In our case, in the previous example, right? Maybe it is similar to the switch on N. We are waiting for the process to end. Well, let me remove this, I guess. Yes. Is it? And something like this. A system will switch when the current process is finished. And if we use switch on IO, the information changes to finish or issue an input-output. So maybe using wait is similar to where is it? Similar to the switch on N, this one. Current process is finished. Okay. We now present this interface in more detail with a few simple examples to motivate us and those our problem. The crux: how to create and control process. What interface should the operating system present for process creation and control? Okay, let me open my note. Do I need to take not on the previous chapter. I think the process lies Person 20. To the individual structure that stores information about the process as process control block. Okay. Maybe we will learn this on the next chapter. Okay. What interface should the operating system present for process creation and control? How should this interface be designed to enable powerful functionality? It's of use in high performance. With the fork system call. The fork system call is used to create a new process. However, before one, it is certainly the strangest routine you will ever call. More specifically, you have a running program whose code look like what you see in figure 5.1. Examine the code, or better yet, type it in and run it yourself. Well, okay, we admit that we don't know that part here. Okay, who knows what routines you call when no one is looking? But fork is pretty odd. Who knows what routine you call when no one is looking? Okay, but fork is pretty odd. No matter how unusual your routine calling patterns are. Let me check in the main page. What is the AM in here mean? Interesting. Let's check. Oh, module. Okay. Module. Maybe that's what AM stands for. Anyway, okay, at least this is a POSIX compliant, I assume. Let's check. Unistd, okay. PID_T, okay. And well, we don't have any parameter. Okay, interesting. Hello PID. Okay, you know what? Let's try this out. What should we call it? P1.c. Okay. Let's call it P1.c. Alright. And then include stdio.h. Okay. For the printf. And then stdlib.h. it. Where are we using this? You know what? Let's try not include this header first and see if we get an error message. Okay, and we didn't provide any argument, right? Let's just use void and 0. Okay, printf. What is get PID? Get process identification. Okay. Okay. PID underscore T. C programming size, I guess. Okay, this like integer basically. Tray, okay. Format. A following integer conversion correspond to a size underscore T. Oh. Okay, for the size T. Now let's check. No. PTFT. Okay. Don't have PID underscore T. Maybe we can use ZU instead. That one. Something like this maybe. Get PID let's find out. P1. Wait a minute. Oh. Okay. CPU intro. Agak ini. Okay. Alright. So we don't really need to cache that integer. I mean, it might differ from the other machine. So keep that in mind. What is RC stand for? Yeah, what is RC stand for in here? Resource. Fork file. Okay, exit. New process. Okay. Oh, wait a minute. Wait a minute. Start. Be something like this. Start and then fork. Okay. Less than 0, it means the fork fail. Alright. Okay. Parent goes down this path. My stomach's fork fail. Okay. And then exit 1. Else if right equals 0. Printf child. Get PID. Oh, you can get the PID of the child. Okay. Then else. Parent of. Okay, interesting. When will we, what is it called? condition, Is it more than 0? Oh, I need to get breakfast soon. Okay, so we need to include stdlib because of for the exit function. Right. Then return 0. Okay. Parent. Oh. Wait a minute. Is the RC gonna change multiple time? Like what? I mean, we are not in a looping, right? So how do we print this tree out? Well, let's find out, I guess. I mean, sure, this is called the start is where we print this out, right? But how can we print this and this? What happened? I mean, we should evaluate this once, right? So it should be either the fork fail, or we print the child, or we print the parent off. And now suddenly it become like this, printing out to information from the condition without any iteration. So what is going on? Right. Okay, let us understand what happened in more detail in P1.c. Okay. When it first starts running, the process prints out a hello message, right? This one. Okay. This is, I think, easy to understand. Right. Hello message. But in my implementation, we use start instead of hello. Include in that message is its process identifier or PID, right? The process identifier or process ID. Okay, the process has PID 29146. In Unix system, the PID is used to name the process if one wants to do something with the process, such as, for example, stop it from running. Okay, right. So far so good. Okay. So yeah, we give a label or a name to the process so that we can stop it from running, to stop the process. Now the interesting part begins. Indeed, it is interesting. The process called the fork system call, which the operating system provides as a way to create a new process. Okay. The odd part, the process that is created is an almost exact copy of the calling process. That means that the operating system, it now looks like there are two copies of the program P1 running. That means that the operating system, it now looks like there are two copies of the program P1 running, and both are about to return from the fork system call. The newly created process called the child, in contrast to the greeting parent, doesn't start running at main. Oh, wait, what? The newly created process called the child, in contrast to the greeting parent, doesn't start running at main, like you may expect. Right, the hello message only print out once. That's why I'm kind of confused, right? If it is the clone of this process, why the start only print out once in this case? Okay, let's continue. Rather, it just comes into life as if it had called fork itself. Fork itself. Oh. Called fork itself. Wait, now I'm kind of curious. If we change this, we are calling fork first, and then we are printing the start. What would happen? Okay, start parent, start child. Alright, so we are, what is it called? We are copying when we call the fork system call, rather than from the beginning of the main, what is it called? Main function. That's why when we do this, right, the start print out twice, not one. Unlike this one, right? We are starting the copy of the process from this line until maybe this line. Yeah, I'm not really sure where is the end of the fork yet, but I'm assuming until the return function. And that make me curious again. Okay. No. I mean, yeah, if we add a lot of this, it's not gonna happen. It's not, what is it called? It's not copying into the child process. Okay, maybe something like this. Print something. Compiling this one, okay. Mana sih? Something and then another something. Okay. I mean, that also make me curious if we return 1 instead of 0, right? I mean, we can think of this as a, what is it called? I mean, 0 in C for the conditional means false, right? And then the non-zero means true. So when we are returning 0, it's like we are asking, is there any error? If it is 0, it means false. There is no error. If it is non-zero, whether 1 or 69, right? It should be an error. Well, let's find out if my hypothesis is correct or not. Okay. Okay, we are not returned from the function. So is the, what is it called? Is the copy of the current process or the fork of the process not execute the return function? Is that it? Not really the return function, the return statement. Sorry. Maybe so. Again, 69, right? So we are returning from the function in this one, but we are still printing the child. Of the fork. Oh, it is interesting. So what happened? I mean, we already return from the main function in here, right? So why are we still executing this one in the child process? There is a lot of question. It is kind of interesting. Okay, calling fork and wait. Okay, P2.c. You might have noticed that that is an exact copy, right? It is not the exact copy, and that's why we have this almost, right? And as we can see, when we print return in here, we are not returning from the function. Something like this. Right? The status code is still fine. So we are executing this child process. Wait a minute. Hold on. Oh, okay. Parent of LC. Oh, okay, right. This is the child process ID. Okay. Child process ID. Okay. I got confused there for a bit. The child isn't an exact copy. Specifically, it now has its own copy of the address space, its own private memory, its own register, its own PC, and so forth. The value it returns to the color of fork is different. Specifically, while the parent receives the PID of the newly created child, the children receive a return code of 0. Differentiation is useful because it is simple then to read the code that handles the two different cases as above. It is simple then to write the code that handles the different cases as above. You might also have noticed, right? The PID of the newly created child, the child receives a return code of 0. Simple then to read two different cases. You might also have noticed the output of P1.c is not deterministic. Okay, When the chat process is created, there are now two active processes in the system that we care about, the parent and the child. Assuming we are running on a system with a single CPU, for simplicities, okay, then either the child or the parent might run at that point. In our example above, the parent did and thus print out its message first. In other cases, the opposite might happen as we saw in this output trace. Oh, we are using the wait. Let me check. Okay, second one. This way. Okay. I mean, if in this case, do we need exit? Or maybe we can just use return, you know? That make me curious again. Difference using exit and return in main. Okay. From main function, okay, this one. Call it from nested function, not just from main. Functionality are equivalent. And when you return to the CRT start code that called main, obviously depend on the operating system and on the C library. In general terms, it of course has to implement all the ISO C requirement equivalent to okay. So either way the same stuff happen. This one in your question. Program start up. Okay, this look like an interesting article. Let me put this in the chat. Okay, I'm not sure. Okay, we will use the light theme here. Okay, interesting. I can really post this as an answer though. The scene what happens at least on some popular operating system is this. By the C standard, a return from the initial call to the main function is equivalent to calling the exit function with the value returned by the main function as its argument. Okay. Unless a certain unless such a statement would be unreachable. Okay. Maybe we can do something like this and remove this one. The STD-lib looks fine. Okay. See, from other function different than main. I mean, we are currently in the main function, so let's just use the return to minimize the dependency that we use. And even if I want to evoke the main, okay, actually there is a difference, but it's subtle. Okay, it has more implication for C++, but the difference are important. When I call return in main, the structure will be called for my locally scoped object. If I call exit, no destructor will be called for my locally scoped object. Does not return. Exit does not return. That means that once I call it, there are no taxis. What is backseas? Any object that you have created in that function will not be destroyed. Often this has no implication, but sometimes it does make closing file. Wait a minute. Okay. I'm assuming the object in this case mean, what is it called? The data storage, like the place we store the data. That is like not that static object. Okay, will be cleaned up even if you call exit. Finally, note that if you use a port, no object will be destroyed. Is no global object, no static object, and no local object will have their destructor call. And favoring exit over return. Okay, interesting. Let me copy this in the chat. Okay, there is a difference between the C library file buffer and the C++ file system object. Exit being part of the C library was designed to coordinate with and flush the former, but can bypass the latter. It is former and latter. First, I'll open output stream. The appropriate destructor is called. As the formal, even standard C++, if stream content is not flashed to this. Linux GCC, okay. And obviously, user-defined types that have buffer input-output can be expect to flash either. But for my locally, it's no longer true for C++ 11 with the current thread storage duration with thread storage duration are destroyed. C++ 11 only. Okay. For other local objects are still not called. This answer can still be confusing for reader using C, right? Is this only C++ or C is also the same? I mean, there is a difference between C and C++, right? Okay, for C, the issue about closing file cleaning is actually wrong. The only time data might not be flushed is in the opposite case. If one use return from main and one has called setBuff with a buffer declared as automatic storage in main, answer, where is R? Below, okay. It really too bad this question is taken with both C and C++. Encoding style, it's not a style issue. It's not a style issue, okay. To take comments and other answer into account. In its current state, it is incorrect and having, for instance, it's mixing up flashing and close, and C input output are flash, while C++ stream aren't. Right, I mean, taking the question with C and C++ can be confusing, right? In C, we make do something, in C++ doing different thing. Having it as the accepted answer is annoying. I don't vote until it is fixed. Not a difference. Exit is a standard library function, so you need to include headers and link it with standard library. I mean, yeah. The same effect as returning 0. This depends. On what kind of executable you are building. What is calling main? Okay. You mean return just when you really mean return, just make the code more confusing. Okay, let's check this out. Oh, this is the duplicate one. We have to open this in this, I guess. Right, in this case, we are only tag with the C programming language, not the C++ one. Then transfer. You don't have to or save or restore the calls, save register, or the return address if the API puts that register that is. What you really think of? Freestanding environment. Depend on the environment. Then returning from main produce undefined behavior but valid. To assign to one of the standard stream an automatic storage to session buffer in main, then returning from main produce undefined behavior. Another potential usage, recursive invocation of main. The standard was where is the error? Is this the comment? Then returning set vbuff or set buff. Let me check. time buffer operation. Buffer. Again, I'm still not sure. Is there any difference we are using return in here or using exit instead? You know what? Let's try using exit in this one. 69. Is that a warning? No, okay. It is still executed. Run or exit, sorry, exit. Register a function to be called. Oh, normal process termination. Normal process termination. Okay. Maybe for now we can do something like this, using return instead of exit function. Maybe since the dynamic storage of main vanishes when main returns, does not vanish if call to exit is made instead. This continuation of execution is usually technically true if you can call your main function. It's not exactly what you mean when you mean to end the process. You want to end your program from without any other function except main. Doing so consistently in main as well makes your code much more readable. For C++, if a throw or a port, especially for it, exit in main. Okay, let us check this one. Let me copy this in the chat. Confirming implementation R. Where should we read the info? Five, one, two, two. Oh, this one. Right. 5, 1, 2, 2, 3. If the return type of the main function is a type compatible with int, a return from the initial call to the main function is equivalent to calling the exit function with the value returned by the main function as its argument. With the value returned by the main function as its argument. Return reaching the that terminates the main function return a value of 0. The return type is not compatible with int. The termination status returned to the host environment is unspecified. With automatic storage duration declared in main, we have in the former case, even where they would not have in the latter. Oh, former case. When we are using return, automatic storage duration will end. They would not have in the latter, which is using function, exit function. So the automatic storage duration is not clean up when we are using exit function. I'm still not sure. Yeah, but this is kind of interesting, you know. Looks like there might be some difference when we use exit or return in the main function. It's just I'm not sure which one is the correct one. Okay, I think we will try this out on the next session. Okay, so that's it for now. Thank you for watching and see you next time. Bye bye.